Welcome back again, dear friends. Once we complete the velocity and acceleration of fluid particle, which is very important in 3D dimensional axis and 2D dimensional axis, and also continuity equation in steady flow. So let us see now continuity equation in differential form. So you have two velocity components are given in the following cases. Find the third component of velocity such that they satisfy the equation, which means the continuity equation. So to satisfy the continuity equation, there are some criteria to fulfill. So if you have a u component, v component, and also here v and w component, so we have some continuity equation, general continuity equation, so that the partial derivative of each component with respect to each axis will be, the summation will be 0. So let us see now. So you have two velocity components. For this case, let us see now. U is equal to minus x cubed plus y squared minus 2z squared. And v x squared y plus yz plus xy. And the third component will be 0. W, we don't have w. Now let us see now. You have u component and v component. So what will be del u del x? Del u del x will be, you have minus x cubed, so minus 3x squared. And del v with respect to del y. So you have x squared. Since you have this is 1, the power of 1, so the derivative will be just x squared only. This is 1. So x squared plus, you have here z, then it will be z. So y will be derivated, so z plus x. So you have del u del x del v del y. So this is the general equation for continuity equation. So it should satisfy this one. So let us see. Substituting the values in the above equation, you simply substitute the values del u del x plus del v del y plus del w with respect to del z. So let us see. Del w with respect to del z, let us see. Del w with respect to del z, you have 2x squared, then minus z minus x. So you have the third component, this is the derivative. So del w is equal to, just you can multiply crisscross. So 2x squared minus z minus x del z. So once you have this equation, now let's proceed integrating both sides. So you can integrate both sides, integrate this one and this. Once you integrate, then you can find this value, which is w. So w is already known. So 2x squared z minus z squared over 2 minus xz plus c. So we have got w function. The third component is this one, because we are asked to find the third component. So how do you get c value? So the constant of integration could be a function of x and y, such that f of xy, or that is f of xy. This we derive the third component as follows. How do you derive the third component? Just you have w is equal to x squared z minus z squared over 2 minus x z, then function of xy. So the c value will be function of xy. Okay, the second problem is, if v is this one and w is this one, how do you get the third component u? So you are asked u. U is how much? How much? So let us see. U, so del v with respect to del y can have minus 4y, then del w with respect to del z minus 2xy. So z will be derivated, then substitute in this equation. So this is the continuity equation. Then to satisfy the continuity equation, how do you calculate the third component? So once you have continuity equation, substituting the values in the continuity equation, then you have this value equal to 0. Then del u with respect to del x, you have this one. Then you can integrate again this one. Integrate both sides. You can integrate. Integrating both sides. Then it will be plus c. So integrate with respect to u for xy, which is u is just function of x. So you will have 4x times y is constant, then x square y. So this is x square over 2, then 2 cancel, then x square y plus c. Thus, we derive third component, this one. U is 4xy plus x square y plus f of yz. f of yz. Okay. The other example is rotational and irrotational flow. Now, let us see if the velocity components of two-dimensional incompressible fluid flow is r u 3x cubed and v minus 5x squared y, then find the shear strain rate. And also state whether the flow is rotational or irrotational. So let u 3x cubed and v minus 5x squared y, then you have to derivate del u with respect to del x. With respect to x, you have this is, you bring this one, 3 times 3, 9x squared. Del u with respect to y, 0. Del v with respect to del x, this is minus 10xy. Derivate this one. Then del v with respect to y, again, minus 5xy. Again, minus 5x squared. Y will be constant. So y will be derived. Then this is as a constant, it will be derived. So the shear strain rate is given by this equation. This is the shear strain rate, which is eta xy is equal to half of del v del x plus del y del u del y equal to half of minus 10xy plus 0. Then you have this one. So this is the shear strain rate, and whether it is rotational or irrotational, you will check this one. The angular velocity with respect to z should be some one. So 1 over 2 del v del x minus del u del y, half of this value. You substitute, then you get this result. So from this result, we can conclude that since the rotation omega c is different from 0, and therefore the flow is rotational. The flow is rotational since omega z is different from 0. Examine whether u y cubed plus 6x minus 3x squared y and v 3xy squared minus 6y minus x squared represent physically possible two-dimensional flow. Also check whether the flow is rotational or irrotational. Let us see the solution. You have to go to same approach. You have u function, you have u function, then v function, then derivate. Del u with respect to x, you have 6 minus 6xy. Del u with respect to y, again 3y squared minus 3x squared. You have here, you can just derivate with respect to y. You get this result and this result. Then del v with respect to x, again with respect to x, you can derivate 3y squared since this is a product. So keep x as a constant, then you can just derive. So you have y is the variable, but x is a constant. X is a variable and y is a constant. So you have 3y squared minus 3x squared. Then del v with respect to del y, again just the derivative with respect to y. So with respect to y, you have to multiply 2 by 3, 6xy. So x will be constant. And here y is a variable, so it will be 6. This is only variable, it will be 0. So you get this result. Then check the continuity equation. Del u with respect to del x plus del v with respect to del y equal to 0. So this is continuity equation. So since we have a two-dimensional flow, we don't need to compute the third component. So substitute these values in the continuity equation, it should make 0. So since the continuity equation is satisfied, it is possible. It is a possible case of fluid flow. Possible case of fluid flow. So you can check now omega z, which is angular velocity with respect to z, del v with respect to del x. Then you can have this general equation for angular velocity in z direction. Then you can substitute half of 3y squared minus 3x squared, then minus 3y squared minus 3x squared equal to 0. Since omega z is 0, then we can say this is just rotational, irrotational flow. Since omega z is 0, therefore the flow is irrotational. So I think this is important. So the other problem is stream function and velocity potential. A stream function, you have p, which is equal to 2x squared minus y squared, y cubed. Determine the magnitude and direction of the velocity components at a point 2, 1. So let psi equal to 2x squared minus y squared, x is equal to 2, y is equal to 1, already given. So let v be the magnitude of the velocity, then v will be negative of partial psi with respect to x. Then you can substitute now. So minus of partial with respect to x, then it's just psi function is given. So you just partial derivative with respect to x. So you have minus 4x. And v is equal to minus 4 times 2. Minus 4 times 2. You simply substitute 2 here. Then you will get negative 8. Negative 8 is the velocity. So once you find the magnitude and the direction of the velocity component, we can go again for other steps. So let u is equal to partial psi with respect to y. Then you substitute the same approach with respect to y, negative 3y squared. So you simply substitute y value, then you get u. So this is u, negative 3 meter per second, and v, negative 8 meter per second. So the magnitude will be u square plus v square. So you have this is the magnitude of the velocity, and tan alpha will be v over u, which is this result. Then you can have alpha, this angle 69.44 degree. So I think with this we can redraw the velocity function and also the stream function so that we can have direction. So the velocity potential function is given by this one. Another problem. The velocity potential is this one. Then determine the magnitude of the velocity components at a point 2, 3. Now let us see. Solution, you have phi, which is velocity potential is given at these points. Now let v be the magnitude of the velocity. Then we can have u partial phi with respect to x, which is just phi is already given with respect to x, you get 6x. So once you get 6x, then you simply substitute the coordinate, which is at x at 2. At 2 later, you have u will be 12. Then v again, you have partial phi with respect to y. Then you have 3x squared minus y squared. Then you get minus 2y. Then you substitute the value of y, which is this result. Then you have minus 6. This is v velocity. Then the magnitude will be u squared plus v squared under square root. So you have this result. Again, you can calculate the direction. So as exercise, you can try this one. In a two-dimensional incompressible flow, the fluid velocity component are given by u y cube over 3 plus 2x minus x squared y, and v x y squared minus 2y minus x cube over 3 shows that the velocity potential exists and it represents irrotational flow. So we will check the previous formula. Then finally, we have to check the velocity potential whether it exists or not. and determine the stream function psi and determine the velocity potential phi. Just from the above formulas, we can apply. You simply just find this value and this value, u and v, then you will check for other steps again. And the stream function also, you have the previous formula with respect to x and with respect to y. Then you can have another approach. Then you will arrive at this point. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it. So please like, share this video with your friends and subscribe to my channel to get more videos on similar examples. And thanks for watching. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it. So please like, share this video with your friends and subscribe to my channel to get more videos on similar examples. And thanks for watching.